Consider the matrix M of the size 2 cross 2 is 1 1 1 0 belongs to M2R, means entries are coming from set of real number. Then the eighth power of M satisfies M raised to the power 8 to 1 0 equals to x y. So if anyhow we can find M raised to the power 8, then we can easily predict the values of x, value of x. So first try to find M square, which is 1 1 1 0, and this matrix multiply by itself give you M square. So M square is 2 1 1 1. Now M raised to the power 4 is multiplied to 1 1 1 with itself give you M raised to the power 4. So this value is 2 is 4 plus 1 5, 2 plus 1 3, this is 3 and 1, not 1 2. Now M raised to the power 8 is 5332 by 5332. 5 is 25 plus 3 equals to 34, and this value 53 is 15 plus 6 21. This value is again 21. 9 plus 4 9 plus 4 13. As it is given, M raised to the power 8 1 0 give you x y. This implies that 34 21 21 13 multiply by column vector 1 0 give you 34, and this is 21, and this is same as xy, so value of x is 34. Option C is correct. The rank of the matrix of the size 4 cross 6 with the entries in real number is. To find rank of this matrix, we will apply elementary row operation on this. After applying elementary row operation, we have an equivalent matrix. So there is no change in first row 1 1 1 and 0 0. Second row is 0 minus 1 minus 1 1 1 0. Third row 0 1 0 1 0 1. Fourth row 0 0 0 1 1. This is our first equivalent matrix obtained by elementary row operation R2 minus R1. Now another equivalent matrix is whenever we will apply elementary row operation on R3, means R3 minus or R3 plus R2. This is our elementary row operation. So what we have, there is no change in first row 1 1 1 0 0 0. Second row 0 minus 1 minus 1 1 1 0. Third row 0 0 minus 1 2 0 1, and the fourth row is 0 0 1 0 1 1. So this is the matrix. Now another elementary row operation we are going to apply on R4. R4 minus R3. So what we have, first row is same, second row is same, third row is also same, and the fourth row is 0 0 0 2 1 2. So first entry of first row, second entry of second row, and third entry of third row is pivot element, and In fourth row, this is the pivot element. So we are getting 4 pivot elements. So rank of this matrix, call this matrix M, is 4. Option D is correct. We be a real vector space consisting of all polynomials in one variable with real coefficients and having degree at most 6. Together with the zero polynomial, in this vector space, zero polynomial is also there. Then which of the following is true? Option A, set given in option A is a subspace. If any set is form subspace, then it is necessary it contains a zero vector or zero element. So consider fx equals to 0. This is zero vector. Now we are checking that this function is in the set given in option A or not. So f half equals to 0, and 0 is a 0 belongs to Q, but condition on set given in option A should not belongs to Q. That's why option A is not subspace. Now for option B, if we consider a zero polynomial or zero function, then fx equals to 0. That's why f half equals to 0, but f half not equals to 1. That's why option B is not subspace. Now in option C, fx equals to 0. So value of f half equals to 0, and f1 is also 0. So these two values are same. That's why 0 vector is in. Now check option D is containing a 0 vector or not. So fx equals to 0, it means f prime x equals to 0, and f prime half is equals to 0, not equals to 1. That's why option D is not a subspace. Only option C is a subspace. You can check scaled property also. So correct option is C. Let G be a group of order 2022 and H and K with subgroup of G. H and K both are subgroup of G. Order of H is 337 and order of K is 674 respectively. If H union K is also a subgroup of G, union is subgroup of G if and only if either union is subset of H or H union K is a subgroup of H. As we know that order is given, and order of union is also a subgroup of G as it is given, and we know that order of subgroup divides order of group. So H union K, order of H union K will divide order of group, and this is 2022. As order of H is less than order of K, this implies that H union K is subset or subgroup of K. It means that if these are subset and these are subgroup, so order of H union K will same as order of K. So order of K will divide order of group, and order of K is 674 divide 2022. 2022 we can write 2022 after factorize by 2, 1011, and using 3, 3 is 9, 1 1, 3 is 9, and 3 7 ja 21. So 2022 can be written as 2 into 3 into 3, 3, 7. And if we multiply 3, 3, 7, we are getting 3 into 674. And obviously 674 divides this one. So it is perfect. Means order of union is 674. Now it is clear. So order of union cannot be 1011. Now option A is saying H is normal subgroup of H union K. To check normal, we try to find index H union K, index with H. This is equals to order of H union K divides order of H, and order of union is 674 divide 337, and we are getting 2. If index is 2, then we say that group is normal. So this is true, option C is true, and asking which one is false. So option B will be key for this problem. K is normal subgroup of H union K. You can find index also. Index of K with union. So index is equals to order of H union K divides order of K, and this index is 1. If index is 1 or index is 2, then always normal. And we know that union of subgroup is equals to K. That's why any subset is normal to itself. Option D is also true. So key for this problem is option B. The radius of convergence of the power series, if series is given a n x raised to the power n, then radius of convergence r can be find using this expression limit n tends to infinity a n raised to the power 1 upon n. As power is given, then power 1 upon n means multiplicative inverse. So radius of convergence of this power series will be 1 upon limit n cube 4 raised to the power n raised to the power 1 upon 5n. So r equals to 1 upon limit n tends to infinity n raised to the power 1 upon n raised to the power 3 upon 5 upon 4 raised to the power 1 upon 5. This value is going to 1, that's why r equals to 4 raised to the power 1 upon 5, or fifth root of 4. Option B is correct. Xn and Yn be sequence of real number defined as you can see on my screen. Then which of the following is true? Xn is convergent, but Yn is not convergent. Xn is not convergent, but Yn is convergent. Means either x1 or y1 is convergent. Both are convergent, and the limit are equal or different. This type of options given in your question. So first, trying to find relation between xn and yn so that we can easily predict either x1 or yn is monotonic or bounded. As we know that xn plus 1, it is given xn plus yn divided by 2, and yn plus 1 equals to under root xn into yn. So this is algebraic mean AM, and this is geometric mean GM. And we know the relation between AM and GM. GM is always less than equals to AM. This implies that yn plus 1 is less than xn plus 1, and you can write yn less than equals to xn. Means all yn or terms of yn, sequence yn is always less than sequence xn. As xn plus 1 equals to xn plus yn divided by 2, and we know that yn is less than equals to xn. If you replace this yn, so what we have xn plus xn, and this will be greater than equals to divided by 2, and this one equals to xn. From this we have xn plus 1 greater than equals to xn, means the sequence xn is monotonic decreasing, and yn plus 1 equals to under root xn into yn. So replace xn, try xn to find a relation between to find a nature of yn. As yn is less than equals to xn, if we replace xn by yn, so yn into yn, this will be less than this one. From this we have yn plus 1 greater than equals to yn, means increasing sequence. So xn is decreasing. Xn is decreasing. That's why x1 is greater than x2, greater than x3, and so on. Xn, and xn is greater than yn. This is greater than yn minus 1. This is greater than yn minus 2, and so on y1. From the questions as given, xn and yn have some point. Xn is 1 and yn is half. So other terms, either x1 and yn, both are between 1 and half. It means xn is bounded as well as yn is bounded, plus xn is monotonic and yn is also monotonic. So xn and yn both are convergent. Monotonic plus bounded implies convergent. This implies xn and yn both are convergent. Now try to find a relationship between limit of xn and yn. As xn plus 1 equals to xn plus yn divided by 2. Suppose limit of xn equals to L1 and limit of yn equals to L2. From this L equals to L1 L2 divided by 2. From cross multiplication we have 2 times L1 equals to L1 plus L2. From this L1 equals to L2. Both limit are same. Now try to find which one option is correct. Both xn and yn are convergent and limits are equal. Option D is correct. An and bn are two sequence and define two series using an and bn, and we have to tell about convergence of series an and bn. For this problem, if a sequence is convergent, if a series is convergent, then its limit of nth term or sequence of partial sum is convergent. For this, we try to solve this problem. So, first summation an, if convergent, then limit of an equals to 0. This is the rule. And an is given to you an equals to 3 raised to the power n plus 3, 5 raised to the power n minus 5. take 3 raised to the power n common from numerator. So 1 plus 3 upon 3 raised to the power n upon 5 raised to the power n, 1 minus 5 upon 5 raised to the power n. From this, you can find 3 upon 5 raised to the power n. This is a geometric progression with common ratio CR less than 1, and this is geometric series. So consider Vn. So Vn, limit of this expression is 1 not equals to 0. So An and Vn behave alike because Vn is convergent. This is convergent. That's why An is convergent. Now we have reached up to summation An is convergent. Now try to find out summation Bn is convergent or not. For this, Bn you can consider as 1 plus n square raised to the power 1 by 4. Now take n square common from denominator. So you can write Bn as 1 upon n square within bracket 1 plus 1 upon n square raised to the power 1 by 4. Also power 1 by 4 here. So what we have? We have 1 upon n raised to the power 1 by 2 within bracket 1 plus 1 upon n square raised to the power 1 by 4. Limit of this expression is finite. Finite and not equals to 0. That's why consider this is a Vn. So Vn and Bn behave alike, behave alike, and Vn is divergent. Vn is divergent because of p less than 1. That's why summation Bn divergent. Now try to find which one option is true. Summation An is convergent and Bn is divergent. Option C is correct. Consider the series as given summation 1 upon n raised to the power m 1 plus 1 upon n raised to the power p, where m and p are real numbers. Under which of the following condition does the above series converges? So if you consider this as a circular part, as a Vn, so this Vn will converge when m greater than equals m greater than 1. Apply P series test as you can observe summation 1 upon n raised to the power m. This is a series and this series converges when m greater than 1. And also 1 upon 1 plus 1 upon n raised to the power p, limit of this when n going to infinity is 1 not equals to 0, means finite and non-zero. That's why vn and this series vn and given series will converge or diverge together. They behave alike. That's why as vn is converging, so this series is also converging for m greater than 1. Option is correct, and in other options, as you can observe, m is not perfect for p series test. That's why b, c, and d, all others are wrong. Let T denote the sum of the convergent series this, and S denote the sum of the convergent series, where the terms of S you can find by these three formulas. And then which of the following is true? We have to tell T equals to S means sum are equal and S not equals to 0. 2T equals to S, T equals to 2S, and S not equals to 0. So whatever the options. First, if you observe the series T, T denote the sum of this first convergent series. So given series is nothing but log 2. 1 minus 1 upon 2 plus 1 upon 3 minus 1 upon 4 plus 1 upon 5. If you observe the second series, so you will find that 1 minus 1 upon 2 plus 1 upon 3 minus 1 upon 4 plus 1 upon 5 minus 1 upon 6. But the terms are rearranged. Whenever we rearrange the terms of a given series, then the sum also changes. So sum S is different from sum T. But these are arrangement of log 2. So T equals to, you can write T equals to log 2 and S. We solve first two terms and put a third term same as, and for next two terms try to solve and put next term same as. So what we have for S, 1 minus 1 upon 2, solve these two, we have 1 upon 2, put third term same as, so minus 1 upon 4, solve next two terms, so 1 upon 3 minus 1 upon 6, we will obtain 1 upon 6, and this will be positive, minus 1 upon 8, and so on. So what we have, you can take minus 1 upon 2 outside, so 1 minus 1 upon 2 plus 1 upon 3 minus 1 upon 4, and so on. This is nothing but log 2, log 2. So this is 1 upon 2 log 2, and log 2 is t. So s equals to 1 upon t, and as we have t equals to log 2 not equals to 0, and also t by 2 not equals to 0, so s not equals to 0. We obtained s not equals to 0, and s equals to 1 upon 2 t. This implies that t equals to 2s and s not equals to 0. Option C is correct. But keep remember, when we rearrange the terms of the given series, sum is also changed. Find the limit of this expression. You can divide this expression into two expression. This is our first, and the second one is this one. So try to find limit of first expression as a limit n tends to infinity, 1 raised to the power 4 plus 2 raised to the power 4, and so on, n raised to the power 4 divided by n raised to the power 5. As you can observe, powers are 4. That's why you can resolve this power into as raised to the power 4. So I can write a limit n tends to infinity 1 upon n within bracket 1 upon n raised to the power 4 plus 2 upon n raised to the power 4 plus 3 upon n raised to the power 4 plus and so on n upon n raised to the power 4. You can write this one. So in compact nature, you can also write a limit n tends to infinity 1 upon n, and also you can write k running from 0 to n, 1 upon n within bracket k upon n raised to the power 4. Now if you apply definite integral as a Riemann sum, so you can replace 1 upon n as dx, k upon n as x, and lower limit will be from k min upon n, this is 0, and upper limit n upon n, it means k max n upon n, that is going to 1. So 0 to 1, x raised to the power 4 dx, and this one is x raised to the power 5 upon 5, and limit is from 0 to 1. So 1 upon 5, we are obtaining limit of first part as 1 upon n. Now we will try to find limit of second part. So first write second part. Second part is 1 upon under root n within bracket 1 upon under root n plus 1 plus 1 upon under root n plus 2 plus and so on 1 upon under root 4n. So this is our second part. Try to find take root n common from all these terms. So 1 upon n outside. So 1 upon 1 plus 1 upon n within square root plus 1 upon 1 plus 2 upon n plus and so on 1 upon. Actually root n we already taken outside, so root 4, and we can write how to root 4 1 plus 3 or 3n upon n within square root. So this is our last term, and we have to take limit n tends to infinity. Now again try to write indefinite integral. So you can put 1 upon n as dx and k upon n as x. So this will be 0 to 3. Why 3? Max value. So k max upon n and limit of this n tending to 0. Value of k max will be 3n upon n. That's why value we are getting upper limit as 3. So you can write in compact nature 1 upon n and 1 upon square root of 1 plus k over n, and k is running from 1 to 3n. So upper limit will be 3 and lower limit will be 0. So we have 1 upon square root 1 plus x dx. So now try to integrate this expression. We have under root 1 plus x upon half raised to the power, sorry, limit are from 0 to 3. So what we have? 2 outside. So 2 minus 1 equals to 2. Now limit of first part is 1 upon 5 and limit of second part is 2. So final we are getting 0.2 plus 2 equals to 2.2. So this is numerical answer type and value is 2.2, and this will be the key of this problem. The sum of this series you can find using either expansion or some technique, but sometimes expand directly make you more trouble. So what is the process? If you observe, this series can be written as by resolving in partial fraction as 1 upon 4n minus 3 minus 1 upon 4n plus 1 and take 1 upon 4 outside. So this series you can write like this one. Now try to write terms, and k is running from, not k, n is running from 1 to infinity. So first term will be 1 1 by 4 outside, and you can write 1 upon 1 minus 1 upon 5. Second term will be 1 upon 4, 1 upon 5 minus 1 upon 9, and then 1 upon 4 outside, 1 upon 9 minus 1 upon 13, and so on. And the last term will be 1 upon 4. Last term will be 1 upon 4, 1 upon 4n minus 3 minus 1 upon 4n plus 1. If you observe, this minus 1 upon 5 cancel out by positive, and the all terms will cancel out. The remaining term from all these expansion, we have 1 upon 4 outside and 1 upon 1 minus 1 upon 4, 1 upon 4n plus 1. When actually we need to find the sum of this series, and this is a partial sum. These are partial sum Sn. So to find sum, we need to take limit n tends to infinity, and that one will be 1 upon 4 into 1 minus 0, and this is 1 upon 4 equivalent to 0.25. Listing subgroup of Z triple line. By the Lagrange theorem, we know that order of group, suppose H is H is subgroup of Z triple line. So order of H will divide order of Z triple line. If group is cyclic, then every factor for every factor of Zn or every factor of group, there exists a subgroup. There exists a subgroup of order that subgroup of order that. It means we need to find factors of J triple line, and to find factor, tau function will help you. So we need to find value of tau triple line, and this is tau 3 raised to the power 3 into 3 raised to the power 3 into 37, and value of this is value of tau triple line will be 3 plus 1, means we add in power and 1 plus 1, so final 8. So number of distinct subgroup of J triple line is 8.
The number of elements of order 12 in the symmetric group is 7. If we are interested to find number of elements of any particular order, so first we need to do partition of this n as Sn. So partition of 7 are 7, 6 plus 1, 5 plus 2, 4 plus 3, and other partition you can do. But in this partition, when 4 plus 3 or 3 plus 4, LCM of 4 comma 3 is 12. So only this partition number of elements or elements of order 12 will exist. It means there will be a permutation of length 4 and a permutation of length 3 will exist, and LCM of permutations we can find using LCM. Sorry, order of permutation we can find LCM of length of disjoint cycles. So only in this case you will have LCM 12. So 4 is repeating once. So factorial 7 upon 4 raised to the power 1 factorial 1, and 3 is again only single time. So solve uh, this expression, you will get to 420. So 420 elements of order 12 will exist in S7.
Let R be the radius of convergence of the power series, given power series, then the value of R square is equal. So for this series, first we break this series into two subseries. So 1 upon 3 plus x square upon 3 square plus x raised to the power 4 upon 3 cube, and so on, plus x upon 5 plus x cube upon 5 square plus x raised to the power 5 upon 5 cube, and so on. When we rearrange the terms, then sequence of partial sum change, but radius of convergence doesn't change. So we have break this power series into two sub power series. So let R1 be the radius of convergence of first one, and R2 be the radius of convergence of second one. So R1 we can write first part in a compact way, 1 upon 3 raised to the power n into x raised to the power 2n minus 2, and n is running from 1 to k is running from 1 to n. You can take k. Similarly, second one we can write summation k is running from x, or I can take 1 upon 5 raised to the power 1, 2, 3. So k and x raised to the power 2k minus 1. It is perfect. K is running from 1 to n. Now, one by one, we will try to find the radius of convergence of first one. So R1 equals to 1 upon limit k tends to infinity 1 upon 3 raised to the power k raised to the power 1 upon 2k minus 2. If summation un x raised to the power n, then radius of convergence n tends to infinity 1 upon un raised to the power 1 upon n as power. So simplified form of this expression will be 1 upon limit 1 upon 3 raised to the power n up, sorry, k upon 2k minus 2, and you can take k common from, if we simplify this one, so k upon 2k minus 2, so k cancel out from this one and 1 upon 2. So limit we are getting 1 upon 3, sorry, 1 upon 1 upon 3 raised to the power 1 upon 2, and this one I can write 1 upon root 3, simply root 3. In the same manner, you can find R2, and R2 you will find root 5. So radius of convergence R will be the minimum of R1 and R2, because of, as you can consider, intersection of group and vector space is a group but a union not. So if we take a maximum, then for max value series may converge or may not be, but for minimum series will converge. So R will be, this implies R equals to root 3, and this implies that R square equals to 3. So value of R square is 3. Consider 4 cross 4 matrix M, and you can observe matrix on my screen. This matrix M you can write 10, 10, 10, 10 column wise, and other entries also 10 plus I4. Sum of these two matrices makes M 4 cross 4 matrix. If anyhow we can find the eigenvalues of this matrix plus eigenvalues of I4, then we can easily predict about the eigenvalues of M. As all entries of this matrix is 10, that's why rank of this matrix, suppose call it matrix A, is 1, and other rank implying that there is one non-zero eigenvalue and other eigenvalues are 0, 0, 0. So one non-zero eigenvalue you can denote by hash symbol, and other three eigenvalues are 0. Eigenvalues of I4 are 1, 1, 1 and 1. So now problem is that you have to find this non-zero eigenvalue. If you find the trace of matrix A as this, so trace will be 40, and trace is 40, and sum of all eigenvalues give you trace. So non-zero eigenvalue is 40. So eigenvalues of M are 41, 41, comma 1, comma 1, comma 1, and product of these eigenvalues is 41. So value of determinant of this matrix M is 41. Also you can find answer using column operations and row operations. In first column, sum of all columns, and you can take 41 outside and apply elementary row operation to find eigenvalues. Also, in this manner, you can find the determinant of this matrix.